So this is problem 7. Find the qualities for the circuit below. So the first step, problem A, is to find the source current. To do that, typically the best way to do it is to find the total resistance. So the first thing you're going to want to do is take RT, right? And you're going to want to recognize that these resistors over here are all in parallel, which means you're going to end up with 1 over 100 plus 1 over 200 plus 1 over 200 again, plus 1 over 25. And then you're going to want to add on the resistors in stage 2 and 1, which are in series with that parallel network. So that's 10 plus 80, and that's going to get you a total of 106.7. Lastly, you're going to use Ohm's law, Vs over RT, and that's going to equal the source current. So that's 30 over 106.7, and that's going to be equal to 0.28 amps. The next step, part B, is to find power in. So there are multiple ways you can solve this one. You can use V times I. That would be Vs times Is. 30 times 0.28. That will get you the answer of 8.4. You can also say P equals I squared R, I being 0.28 squared, R being 106.7. It will give you the same result of 8.4. You can also use the V squared over R equation. I don't have enough room here, but it gives you the same exact answer, whichever one you prefer. So the next step is to use the current divider rule to find I1, I2, I3, and IL. So we'll start with I1. So the first thing you're going to want to write down is the current divider rule. That is on your equation under CDR. And you have IX equals IEQ. And that's going to be REQ over RX. Now, RX is the resistor of interest. IX is the current that flows through that resistor. REQ and IEQ refer to the parallel network. Now, only the parallel network, which means you're not going to use RT in this case. You would want to use this section that I'm coloring in red. REQ is equal to just that parallel section. So 1 over 100 over 1 over 200 plus 1 over 200 plus 1 over 25. And that's over -1. And just plug that in your calculator. It'll give you 16.67 ohms. All right. Now it's just a matter of plugging it all in. IEQ is the current that goes into that parallel network. That is IS. So that is the number we used in A. So I1 will equal 0.28 IS times IEQ 16.67 over the resistor that I1 goes through, which is 100. That would give us 46.7 milliamps. Same process for the next one. Same IEQ. Same REQ. Just a different RX. and that'll give us 23.34 milliamps. Now, you're going to notice that the 200s are connected to each other in parallel. They have the same IX value because they have the same IEQ, same REQ, and same RX value, which means that this also equals I3. Lastly, IL, same IEQ, same REQ, and a different RX of 25. And that's going to give us 186.7 milliamps. And that's part C. Part D is to find the losses in each stage. Now, if we look up here, the stages are defined by these red sections, and all we need to do is find the power of the resistors in those sections. So for stage one, it's just going to be the 80 ohm times its current squared, which is IS squared. So that's 80 times 0.28 squared. And that equals 6.272 watts. Now, for stage two, we have a little bit more going on because we have this 10 ohm, which has IS going through it, but then the 100 has I1 going through it. So that's going to be the power plus 2 is going to be equal to the power of the 10 ohm plus the power of the 100 ohm, right? And remember, we're using the P equals I squared R equation. So that's going to be the 10 ohm times the current going through it squared plus the 100 ohm times the current going through it squared, which is I1. And that's 10 times 0.28 plus 100 times up here, it was 0.046 squared. And that's going to equal about a watt. Lastly, we've got power at stage three. And that's going to be the power of those 200 ohm resistor together. So that's pretty easy. P loss 3 is going to be the power of the 200s plus the power of the other 200. They're the same thing, right? They have the same current, remember, because I2 equals I3, and they have the same resistance value. So we can just double it. So we have 2 times 200 times I2, which is 23.3 times 10 to the negative 3. That's squared. And that's going to give me 0.22 watts. Great. So part E. Now part E is just power out, and that's usually just the power that is located and associated with the load resistor. So that's just the same process you use for the other loss powers, except now it's IL and RL. So we've got 25 times 186.7 times 10 to the negative 3, and that's all squared. And you're going to end up with 0.87 watts. Now, efficiency total is always just going to be the power out times or over the power. So that's 0.87 over the power n that we found in step B, which was 8.4. And that's going to be roughly 10.3%. To find the percentage, you just multiply that fraction by 100. So in part G, we're going to calculate the efficiency of each stage. So efficiency 1 is going to be P out 1 over P in. Now we define P out in this problem as P in minus the loss at that stage. So we're going to have P in minus P loss 1 over P in again. So that's 8.4 minus, what was the P1? It was 6.272 over 8.4 again. And remember, we're going to multiply that with 100 to get our percentage. And that's going to be about 25.3%. The next one is going to follow a similar method. So remember, as it moves through the circuit, it's going to have less and less P in, right? Because you're going to say that P in is going to be whatever's left over at that section of the circuit. So at this point, we've gone through section 1. So we have to subtract it from the original P in. So now we would say it'd be P in minus P loss 1 minus P loss 2 over P in minus P loss 1. And that's going to give us the value that we want. So that's going to be 8.4 minus 6.272 minus that 1 watt. And then that's again 8.4 minus 6.272. And that's going to give us roughly 52% at that stage. And the same thing for stage 3. Now remember, stage 3, you've lost 2 sections worth of power. So your P in is going to reflect that. P in is going to be subtracted by the losses at the first 2 stages. And then finally subtracted by the loss at that stage. So running out of room, so you just plug all this in the calculator, and you would get roughly 80.7% for that stage. Now, this last one is a bit of a concept question, but if you got the right answers for all 3 of these, then they should just multiply together without you having to really know too much. So NT should equal all of these multiplied together. So that's 0.25 times 0.52 times 0.80. And that's roughly going to be equal to our 10.3, which is right. So yes, multiplying all those together, those stages, will get you the correct answer. And that is problem 7.